Hello, today we are going to move to section 11.2. In this section, we are going to talk about three notations. Those three notations are Big O notation, Big Omega notation, and Big Theta notation. And this is chapter 11, where we learn analysis of algorithm efficiency. This is a long section, so I'm going to split this into two classes. This is the first part of the section. This is the first slide. Let me read that. The symbols theta and omega are the uppercase Greek letters theta and omega. The theta notation introduced in this section is determined by ranges such as those shown in figure 11.2.1. So let me mark these ranges, and this is the first range that we're going to discuss today. And then this is the second range. Alright, so these are the two ranges we have here. Alright, the first range is for insertion sort, and the second range is for the merge sort. These are the two sorting methods that we are going to learn in this chapter. Since we are going to learn these methods, I'm not going to give you a lot of information here, but I'm going to give you a small summary. First summary is for the insertion sort. Insertion sort. All right. This is a simple sequential sorting algorithm. A simple sequential sorting algorithm that builds the final sorted array on one item at a time. Okay, that's insertion sort, and then go to the merge sort. Which is a binary algorithm. This is a binary algorithm, which is the merge sort. Merge sort is a binary algorithm, a binary. All right, it's a binary algorithm. The approach that we use is divide and conquer. Okay, a binary algorithm that uses divide and conquer approach. All right, so those are the two summaries of the method that we're going to learn with details later. Here what we are showing is worst case time to process the array. So let's say you are given an array. You can just consider arrays of different lengths. You could just consider arrays of different lengths. Okay, for that given length, you can compute the worst case time. Worst case time for processing the array. That means sorting the array. Okay, you see that the insertion sort has highest worst case time of processing the array. Okay, highest time means least performance. Okay, it is computationally expensive. This method is computationally expensive than that method. That's why this range is above that range. All right, so this is the basic concept of computational complexity. So these two methods, insertion sort and merge sort, are doing the same job. They are sorting a given array, but the thing is computational efficiency is different from the method to method. Okay, if I were you, I would use the merge sort because it is less computationally expensive. Okay, so that's about the first introduction slide. And let me go down. It is related to two other notations. These two notations are omega and O. Okay, at the beginning we talk about theta. As you remember, we talk about theta here. That is given in this figure. All right, that's what we have discussed is theta, and then now we are going to talk about another two notations. Those two notations are omega and O. All right, so we are going to learn all the three notations in this section. All right, so let me read this. The oldest of the notations, the oldest notation here is Obigo notation, was introduced by the German mathematician Paul Bachmann in 1894 in a book on analytic number theory. And it was the first to be used to compare efficiencies of algorithms. All right. As you will see, however, using O notation alone can produce ambiguous or even misleading results. All right. So here you have three notations. Among these three notations, some notations are not accurate. All right. Some notations are not accurate, and some notations are accurate. As an example, O notation and omega notations are not much accurate, whereas theta notation is accurate. All right. So that's why I'm saying here. O notation alone can produce ambiguous or even misleading results because that's not accurate. Okay, this is O notation alone is not accurate. All right, go down. As a response, in 1976, Donald Knuth, a pioneer in the analysis of algorithms, introduced the omega and theta notations so that the growth of functions could be compared with greater precision. All right. The idea of the notations: suppose f and g are real valued functions. F and g are real valued functions of an integer variable n, and suppose that gn is greater than or equal to 0 for every integer n, for every integer n greater than some positive number, then we have these results. All right. Now we are going to introduce two notations with the definitions. These are the definition. The first notation that we're going to introduce is omega, and the next notation we're going to introduce is big O. Okay, so these are the definitions. You have first definition, you have the second definition. All right, let's see how to read these definitions. The first definition is for omega. If For sufficiently large values of n, the values of f are greater than those of a positive multiple of g, then f is of order at least g. And we write this as, fn is order omega. So fn is order of g. All right. So this is how you write it. Fn is a function which is of order gn. All right. So this is how you write the omega notation. Let me explain that. I can easily explain this one by using this graph. Let's say you have a function f which gives you the computational complexity of an algorithm. Let's say you have an algorithm here. Okay. You have an algorithm, so that algorithm has these steps. Okay, so you can compute the complexity of this algorithm as a f. F is the let me put as f of n. F of n is the computational complexity of the algorithm for some n. Okay, so that is this function. So that is this f, the function f. Computational complexity varies like this, right? And then let assume that you can find a function g. You can find a function g such that let me color that. The values of f are greater than those of positive multiple of g. And then let's say you found a function g, and then you multiply g with a positive number. Then you multiply g with a positive number, so you get ag. Then the graph of f should be greater than graph of ag for some large n. Okay, for sufficiently large n. Okay, so that's what given in this graph. At the beginning, the complexity varies. The complexity varies, which goes up and down, but in a later time, the computational complexity is always greater than a times g. It's always greater than a times g, right? So if this happens, we say this function, which is f, is omega of gn. Okay, omega of gn. In words, how do you read that? F is of order at least g. Let me color it by different. This, how do you call this? This is f is of order at least g. All right, the same thing given here. Same thing given right here. That's the notation for that. Okay, I assume that you can understand. This might be a little bit confusing, but just read the definition so you can understand it very well. Okay, that's how you define the omega notation. And then go to the big O notation. Same thing happens here. You have an algorithm, all right, and then you have this function for that algorithm, which gives the computational complexity, all right, and then you can find a function g. You can find a function g. B times g is always greater than f for some sufficiently large n. For some sufficiently large n, which is given right here. Okay. For sufficiently large values of n, the value of f are positive and less than those of positive multiple of g. Okay, let me color that. Values of f are positive and less than, all right, less than, that means it is less, you see. The computational graph is below, here it is above, so that's why we say greater than. Now it is below, we say less than. All right. Less than a positive multiple of g. Here this is the positive multiple of g, bg. Here it is bg, positive multiple of bg. And then how do you read this? We call f is of order at most g, and we denote that by this. This is how you denote the computation complexity in terms of the big O notation. All right. For the big O notation, you have to bound the given function above. You have to bound the given function above. See, blue. This one is the given function. You bound it above. For the omega, this is the given function. You bound it below. Okay, this is below, bounded below. So that's how it works. For omega, you bound below. For O, you bound above. Okay, keep that in mind because you need that knowledge later. All right. Let me move to the next slide. In the next slide, we are going to talk about theta notation. We have already discussed omega and O. Now we are going to give you the definition of the theta notation. If for sufficiently large value of n, the value of f are bounded both above and below by those of positive multiple of g, then f is of order g, and you write it as fn is omega of g of n. All right, so let me explain that along with the graph. And in this case, if f are bounded both above and below by those positive multiple of g. Okay, so this is b times g, which is a positive multiple of g. This is a times g, which is a positive multiple of g. And then what we do here is we just bound it by above and then it by below. Okay, you bound the function of f by above and below, and then we say that f is of order at g. Okay, and then we write it as this. All right, so this is the corresponding plot for that. This is the graph of the computational complexity, and then you can bound this graph above and below by two multiples of g whenever n is greater than some value, when this x-axis is greater than some value, okay, which is given here is n. Sufficiently large n, this bound will occur. Okay, let me think. That is called the theta notation. All right, so let's go down. Now we have all the three definitions in one place. We have already learned this, but let me just read this. Let f and g be real valued functions defined on the same set of non-negative integers with gn is always greater than or equal to 0, and for every integer n greater than or equal to r, where r is a positive real number. Let me highlight some important things. That is important. and this is important. All right, and first point, f is order at least g. F is order at least g. We write that as that. Then what happen is fn is bounded by a times g. Okay, g is any function, and then multiple of a of g is a times gn. Then fn is bounded below by a gn. That is the definition of notation omega. And then number 2, f is of order at most g. We write this as that. All right, and what happened here is now fn is bounded above by a multiple of gn. Okay, if fn is bounded above by multiple of gn. In the third case, f is of order g, and then we write that as that. In this case, fn is bounded above and below by multiple of g. All right, so this is very easy. So there are 3 notations. Now you know the definitions of the notations. Let move to this example. This is example 11.2.1. The problem is this: use theta notation to express the statement. This is the given statement to you. All right, for every n greater than or equal to 3, that means for every n greater than or equal to 3, for every n greater than or equal to 3, this condition is valid. This condition is valid. Okay, that means this function is bounded above by that, which is bounded below by that. Okay, that is what is given by this algebraic expression. Okay, so this is the upper bound. This is the lower bound. Okay, it has upper bound, lower bound. So you have to just write the notation for this blue colored function, the theta notation. You write the theta notation for this function. All right, so let's go forward. And in the solution, I just initialize a as 4 because 4 is right here. You see, 4 is right here. So a is 4. And I initialize b as 30 because 30 is right here. And I initialize k is 3 because n is greater than or equal to 3. Okay, so this is k in that case. That is that. All right. And then I just rewrite the given statement like this. I rewrite the given statement like this. And this is valid when n is greater than or equal to k, because our k is 3. Okay, now go to the definition of theta. This is the definition of theta. So you have this function gn, and you have the same function over there, which is gn. This is a times gn, this is b times gn. A, b are constants. Okay, now it is c. This is like gn. N to the power 6 is like gn. N to the power 6 is like gn. This is like gn. That is like gn. Okay, and this is like fn. Alright, so this is same as this notation, this condition right here. Okay, so a times gn and b times gn. Fn is bounded by a times gn and b times gn. So the order of this one is actually g. Order of f is g. Okay, that means order of Fn is Gn. Order of Fn is Gn. And we write it as that Fn is theta of Gn. Right, so that's right here. This is Fn. This is, let me mark like this. This is actually theta, theta. Theta times G of n. Alright, so it's clear to you now. We are simply using the given definition. Alright. Now go down. We move to the next example. Example 11.2.2. Part A of the problem, use Obigo notation to express the statement. This is the statement given to you. For every n is greater than or equal to 2. That means this condition is true when n is greater than or equal to 2. So now you have to use the Obigo notation to express the statement. In the next case, this is the statement given to you, the algebraic statement, and this is true when n is greater than or equal to 1. You have to use O notation to express that. And finally, you have to justify this is theta of n square. Okay, so these are the given parts. For the first case, you have to use omega, then omega, big O, and finally theta. All right, so just go down. I have written down the solutions right here, so you can read and understand. I'm also going to explain the same thing here. In the first part, you have to recognize what is A, the multiple. Here the A is this, which is the multiple. Okay, now that A is right here. And then you have to recognize this, which is just A, here which is just A. All right, if you, after you recognize this uppercase A and lowercase a, you can write the same expression like this. All right, it is for every n is greater than or equal to A. Now go to the definition of omega. This is the definition of omega, that one. So Fn should be bounded below by that. Fn should be bounded below by A times G. All right. All right, you see. Now this is like G of n, and of course Fn, which is right here, which is bounded below. Okay, which is bounded below. That's by the definition. That means by the definition, for this one you could write this function is omega n square. N square is G here. This is very easy. We are just following the definition. We are just following the definition, okay? So this means omega G of n. Omega G of n. Let me correct omega. All right, this is same as f of n. And let's move to the next problem. In the next problem, we take that as A, and we take, let me mark it as B. We take this as B, and we take that as simple B. Okay, in that case, this is B, uppercase B, this is lowercase b, which is 1. And then you can write this statement. Here, this is same as g of n, that is same as f of n. All right, and then just go to big O notation. Just go to big O notation in the definition. And this is for the big O notation. In this case, you have to bound this function above, bound f of n above by b times g of n. Okay, so you can see that it is bounded above. All right, then we could write, by the definition, this is which is f of n is O of n square. Okay, this is similar to O of g of n. Okay, let's move to the part C. In part C, you have to justify this condition. Let's go to part C. In part C, we have already shown that A is this, uppercase A is this, lowercase a is that, and B is this, lowercase b is that. Let me mark with the same colors. A, I use red for A, uppercase A, and B, that is that, lowercase a, lowercase b. All right, and then you have this n is greater than k. All right. In the first case, it was 2. In the second case it was 1, 2 and 1. All right, which is right here. K can be either 2 or 1. So you could choose the biggest among them, that is 2. You can choose the biggest among them, that's 2. And then you could write the given expression like this. All right, and then this is your g of n, that is your g of n, and this is your f of n. All right, and then this k, take k to be 2, because previous time it was either 1 or, in one case it was 2, in the other case it was 1. So it's better to get the largest among them. All right, so which is 2 here. And then I say by the definition of theta, you could write this function, which is f of n is that which is theta g of n. Okay, that's part C. Part C is actually an implementation of part A and part B. Okay, we have completed the example, and let's move to the next slide. There's a theorem here. We are not going to prove the theorem. Let's read the theorem. If f and g are real valued functions defined on the same set of non-negative integers, and if fn is greater than or equal to 0, gn is greater than or equal to 0, for every n is greater than or equal to r, where r is a positive real number, then if n is theta of g of n, if and only if fn is omega of g of n, and fn is theta 0 o of g of n. Okay, so this is the same. This theorem is very easy. We have already learned this theorem. What this says is, if these two conditions happen, give me a second. If and only if means if these two conditions happen, that will happen. Okay, if this condition happens, that will happen. Okay, that's true. If these two conditions happen, that will happen. If these two conditions happen, that will happen. This is very easy. We have learned that. Occurring this one means you have this case, you have the given whatever the function, which is for the computational complexity. Let me use different colors to show you the difference. All right, let me use different colors. Let's say this is worst case complexity, and that is n. Let's say this is the function for the worst case complexity, which is f, and then omega means this is bounded above by a function. This is bounded above by a function, and which is also bounded below by a function. All right, bounded above and below by a function when n is greater than this n, when you have a sufficiently bigger n. Okay, so that means let me use the same notations like I used before. Upper one is bg and the below one is ag. All right, that means f is bounded above by bg and bounded below by ag. Bounded above by bg means f is given by the or notation. Bounded below by ag means omega notation. Okay, that means this implies that. Let me write it clearly. This implies two cases. The first case is this. The bounded below case that plus the bounded above case. All right, this is f and that is bg. Okay, this implies this single graph implies those two graphs, and those two graphs implies the single graph. Let me make it small. That is just the theorem given here. All right. All right, good. So you understand the theorem. Then go to the next slide. Order of power functions. The functions that are most commonly used for comparing algorithms efficiency are power functions. You know, these are the power functions. Exponential or algorithmic functions, that those are 2 to the power n, log n, and combinations of them. That means n times log n, or maybe n square times log n, and so forth. All right, so you might have seen these functions I used to represent the complexity of an algorithm. All right, so those are the commonly used functions. I'm just expressing these things because you might need these later. Okay. These functions arise naturally in the analysis of algorithms, but for large values of n, their sizes are dramatically different. In this section, we focus on power functions. In this section, we only focus on power functions. Keep that in mind. Okay, that is this case. We only focus on that. All right, and then we have a theorem right here. For any positive rational numbers as r and s, and any integer n is greater than 1, greater than or equal to 1, if r is less than or equal to s, then n times r is less than or equal to n times n to the power s. Okay, so let me read this again. This theorem says n is greater than 1, and if s is greater than r, then n times n to the power s is greater than n to the power r. Okay, this is clear to you. This only happens if n is greater than or equal to 1. When n is smaller than 1, this does not happen. Note that this doesn't hold when n is less than 1. Alright, so this is important. Alright, let's move to the next slide. Now we are going to show some plots of polynomial functions. Let me read this first. The following two examples show how to use theorem 11.2.2, which is right here, which is the theorem, to find big omega and a big O for some polynomial functions. All right. So this theorem says this. Give me a second. This theorem says for n is greater than 1, greater than or equal to 1, if s is greater than r, then n times s is greater than n times r. That means when the power increases, the graph, the power, y to the power, y equals n to the power a. This is the power. Okay, a is the power. This a is the power. When n is greater than 1, you see it is greater than 1. N is greater than or equal to 1. When n is greater than or equal to 1, when the power increases, the graph increases. The graph increases. The graph increases means something like this. Let's say that you have two a values. One a value is less than the other a value. Let's say a equals half and a equals 1. Then n to the power 1 is always bigger than a to the power half. Okay, when n is greater than or equal to 1. If you could put the equal sign, you could put the equal sign when n equals 1. When n equals 1, this left hand side equals that right hand side. Otherwise, it is always n to the power 1 is always greater than n to the power half. That's what I want to say. When the power is bigger, the graph goes above than the other function. Okay, so let me delete this. See, it is 1/3. Okay, this is half, which is half is bigger than 1/3, and 2/3. 2/3 is bigger than half. This is the power is 1. Power is 1. All right, and the power is 3/2. Power is square. Power is cube. When the power increases, the graph goes above the other function. All right, so this is what I want to show you. This is simply theorem 11.2.2. All right, let's move to the next example. Example 11.2.3. You are given two problems. First problem and the second problem. In the first problem, you have to show that 15 n to the power 3, 11 n to the power 2 plus 9 is omega n to the power 3, omega of n to the power 3. When it says omega, you have to upper bound. You have to keep that in mind. When it says omega, you have to upper bound this is f of n, upper bound f of n by some constant times g of n. Here g of n is n to the power 3. A times n to the power 3. All right, good. So that's what we have to do for the first part. Okay, I have given the detailed solution, so you can read that. Let me read it for you. To show that this is that, you need to show that this is greater than or equal to a positive multiple of that. That is this. Okay, that means the upper bound case. You have to show that f of x is upper bound by a times n to the power 3 for all values of n that are sufficiently large. All right. Now what we do? Actually, I made a mistake here. I'm sorry. Let me make the correction. This is omega notation. This is omega notation. This is omega. For omega, it is not actually upper bound. It is actually lower bound. Okay. For omega, it is lower bound. For big O, it should be upper bound. Let me make that correction. So this should be not upper bound, it should be lower bound. You can remember this. I know you can remember this, lower bound. For big O, it is upper bound. All right. So then I already read this. You have to make it greater than or equal to positive multiple of that. All right. You have to make a lower bound. Making a lower bound is very easy. How do you make a lower bound for this function? How do you make a lower bound of that? That is simply, you could just write 15n to the power 3. This will be a good lower bound. Why it is a lower bound? You know, this you could cancel that with that, and this is always greater than or equal to 0. Okay, this is always positive. Okay, this part is always positive. That means for this function, you can make a lower bound like 15n to the power 3. All right. Since the remainder, this part is always positive, this condition is true. This is always, let's say, greater than or equal to 0. All right. So this is the lower bound, which is given right here. For every n greater than or equal to 1. All right. Now you have to understand what is A. You could say this is A, and you could say this is simple A. This is capital A, that is simple A. All right. You have the simple A, capital A both. Then that is actually omega notation. If you go back to the omega notation, it should be here. What we are doing is we have to bound it below. It is all the way at the beginning. The omega notation, we have to bound it below. Okay, we have to bound it below. See, that is for the omega notation. All right, go back to the place where we stopped. All right, so then we can write this function, which is the given function, that is actually this is omega g of n. This is f of n, right? So that is the omega. That is how we put that into omega notation. In part B, we have to show that is again the function which is f. The function is right here. This function is also O of n to the power 3. O of n to the power 3. Okay, let me move to the next slide. For O notation, you have to use the upper bound. Okay, let me copy this. Oops, sorry. Now it is that. Now you have to show it is not lower bound, it should be upper bound. Okay, you have to show it is upper bound. Alright, go down. Now we have to make an upper bound for this function. The function is 15 into the power 3 plus 11 into the power 2 plus 9. We have to make an upper bound for this. So what I could do is I could just write this as this. I put 15 n square, and then I change these to something like that, which is 11. I made a mistake. Sorry, I made a mistake. Let me correct that and explain you from the beginning. 15 into the power 3 plus 11 into the power 2, 9. So you have to make an upper bound for that. First I write 15 into the power 3, and for that part what I'm going to write is 11 into the power 3 plus 9 into the power 3. All right. 9 into the power 3. So this can be simplified as 15 plus 11 plus 9 is what is that, 35? Yes, it is 35. 35 into the power 3. So this is a good upper bound. Let me write it again. 15 into the power 3 plus 11 n square plus 9 is bounded above by 35 into the power 3. Okay, so you could use that relationship to make the upper bound. And this is, let me use a different color to circle that. Whatever circle here and you have the replacement over there. Okay, so you just replace like that. Bigger replacement. Okay, it's a bigger replacement. All right, so that is actually given in this slide. In the next slide, I have shown it is bounded above by 35 n to the power 3. But here I am showing some other aspects. Here I am showing whether it is positive and all. So you can read and understand this part. The most important part is just taking this upper bound. Alright, I say I have already taken the upper bound. And then I could write this as that. I have the upper bound right here. You could treat that as B, and you could treat this as simple B. Let me mark for this, let me mark this to be B and B. Give me a second until I find something quickly. Oh yeah, I found that, not that. What I'm talking about is this. Let me put B for that. Usually I put B for this. B n to the power 3. It's bounded, upper bounded by B times n to the power 3. Alright, go down, and this is that B. This is that B. It's just a notation, don't worry. Previously I used A, now I use B to distinguish. Don't worry about these notations. Alright, so then I write this function which is f of n, and for that I write O notation because it was bounded below, sorry, bounded above. O notation O of g of n. Alright, so this is how you solve the part B of the given problem. These two problems are easy, don't worry about them. Okay, just read them, you can understand. These two problems are easy. In the first case, you have to make the lower bound. In the next case, you have to make the upper bound. Making lower bound is very easy. Making lower bound is very easy. Alright, but making upper bound might be a little bit tricky, but it's of course easy too. Okay, this is here you are making the upper bound, which is a little bit tricky. Making the lower bound is super easy. Okay, so if you get a problem from this section, of course that problem should be very easy for you. Alright, so that is the end of the first part of this section. Let's meet on the next day. Thank you very much.